Hi, this is Eric Goubault, and I'm going to present our case study paper on reinforcement learning for quadcopter attitude control. So the objective of this talk is to fully describe how we design a controller using reinforcement learning for such a quadcopter as the Crazyflie 2.0. And so explaining everything from modeling to the choice of the hyperparameters. Also, the other objective is to assess how well these controllers can be trained under a variety of conditions, both nominal and non-nominal. Non-nominal being two cases here. The first one is a case when you can have a power loss on one motor, and the other one is when you can have wind gusts coming in and change the dynamics of the quadcopter. So first, let me give you some hints about how the modeling goes and what is the classical sort of PID control that we will compare things against. So the dynamics of the quadcopter is based on classical Euler-Ingalls equations on these 10 state variables. So we are interested basically in the altitude Z and in the attitude. So we're going to try to control the roll, pitch, yaw rates PQR. And you see the angles, the pitch, roll, and yaw, phi, theta, and psi occurring in the equations. So S is just an abbreviation for sine and C for cosine. So the action on the dynamics of the quadcopter is through the vertical thrust, so the sum of the four different thrusts of the four different motors, and is through the difference between the thrust on each motors, which induce moments mx, my, and mz around the axis x, y, z, giving some control into roll, pitch, and yaw. Okay. So instead of controlling directly the angular rate of the motors themselves, the PWMs, the pulse width modulations, we're going to control some linear transform on the PWMs. So thrust is the sum of the four PWMs, and common phi, common psi, and common theta are some barycenters of these PWMs. So just to understand what they are really, common phi for the roll, it's a combination of plus the PWMs on motor 1 and motor 2 minus the PWMs on motor 4 and motor 3. So it's looking at the difference between left and right thrust so that you see how the roll rate can be controlled through common phi. So then the vertical thrust and the moments are going to be quadratic in the PWM, so quadratic in these four variables: thrust, common phi, common psi, and common theta, as you can see here. So C1, C2, CT, and CD are constants that have been determined for the Crazyflie 2.0. They are actual, the real constants for this platform. Okay, so we actually compared our training to two different PID controllers. The first one was used at some point in some version of the firmware on the Crazyflie. And the second one was actually cooked up by us. It's a bit less stable, but then it's more aggressive because this one is pretty slow and we were too good somehow with respect to this slow PID. So we wanted to show what we could do with a almost unstable PID, but very aggressive one, and compare the performance between these controllers. Okay, but still we're going to keep the control using a standard PID on thrust. We're just going to try to learn the command phi, command theta, command psi. So nominal mode is kind of obvious. Non-nominal modes will be defined as follows. We're going to saturate the PWM on motor 1 up to 80% at some moment during flight. And the second non-nominal mode will be wind gusts. And so these wind gusts W will create forces on each of the blades here. And this force is going to be bilinear in the angular rate of each motor, omega 1 to omega 4, and in W, the wind velocity of these wind gusts. So you see the formula here. The K encodes this bilinear form. It's a drag coefficient matrix. So it creates a drag force on each of these motor blades, the sum of which is going to be added to the equations we had before, to the linear velocities derivatives. And the differences between these drag forces on each of these blades are going to create extra moments. We have to put in these differential equations for angular rates. Okay, so how are we going to train a controller using reinforcement learning? So here's the schema of what we've been doing. So first we have to decide, I mean, the reinforcement learner is going to try to see which actions, which commands, command phi, command psi, command theta, you have to use on a given state of the quadcopter to reach some target state. So you will have altitude and attitude queries, and given some observation on the state, you're going to decide of actions. So of course, the obvious choice is to use the Markovian states, the full information, which is going to be 7-dimensional. But we'll see that it's actually better to restrict to some sub-dimensional space. It will give better performance. So non-Markovian states can be interesting. And in the literature, you can also find that adding some history, past history, can be interesting to smoothen the action as learned by the reinforcement learner. We won't use history in here, we won't need that. In case of non-nominal training, we'll add some knowledge of the saturation for the partial motor failure and of the wind gust magnitudes that we can measure both on ground and actually directly on the quadcopter sometimes. Okay. So the reinforcement learning will try to find the right actions given these observations, but it will try to maximize some reward. So it will try to do some sort of optimal control with the dual reward, which is the cost function. And the reward we have chosen to use is just basically the clipping of the one norm of the difference between the target angular rates with the current angular rates, which are always part of the observation states. We have also to choose an architecture for the training algorithm to see which weights it should act on. So we're going to use a very simple multi-level perceptron kind of neural net with ReLU activation function, except for the output layer, which uses an hyperbolic tangent for rescaling. So there are other choices in the literature. It's not quite clear that you have such a significant difference if you used some smooth activation functions, for instance. And we haven't observed so we just report things on the ReLU activation function. We have also to decide of the size and of the neural net. It's very scarcely reported in the literature. And so we have gone through a various number of layers, from 1 to 4 hidden layers, and a various number of neurons per layer, from 4 to 64 neurons per layer. So it includes the sizes reported in the literature, but it goes much further and looks for many different solutions to the reinforcement learning problem. We have also looked through different algorithms. So the most interesting ones were DDPG, SAC, TD3, and PPO. Actually, PPO has proven to be less effective, and DDPG, SAC, and TD3 are really have been designed for precisely this sort of control problems. We are training algorithms for continuous states and action spaces, which are very convenient for this control problems. It's not the case for PPO, but still we compared with PPO. So of course we have to feed in data. So we have to feed it with the initial states and query signals. So we have designed a specific query generator that prescribes some angular rates varying from 0.1 to 1 seconds, and with a given magnitude between -0.6 and 0.6 radians per second. And we trained per episode of 1 second, pretty short episodes, but up to 10 different target angular rates. And the queries are going to be independent on pitch, roll, and yaw rates. So of course, this will go through a simulation of the dynamics, and for each action that the current neural network will try to feed in the dynamical model, it will see the reward and update the neural nets to optimize the reward over the 1 second episodes. Okay, so that's for the training. And at the end of the training, we'll have plenty of neural nets, and we are going to see which are the best. So we have to evaluate the performance of these neural nets. And one of the also novelty of this paper is to propose some sort of formal specification of this evaluation process. So we actually used um, uh, um, an STL-based formal description of the performance of the neural net controllers, which will observe what happens with a given neural net controller on 20-second episodes, which will be random episodes chosen with a similar query generator as we had for training, the reinforcement learned neural net controller, but with actually easy to hard queries, actually much harder queries sometimes than the ones we use for training. And basically the performance evaluation will try to see a certain number of formal properties, and the ones we consider in this paper are just some formal specification of the rising time. So you see in red the query signal, the plateau during which takes t seconds, and in yellow what the controller does. And we're going to try to define formally and observe for each of these training, each of these queries, to see the rising time, so going up at least gamma q, so just below the query q by a factor gamma. So what is the time, and measure the average of such times. We're going to try to observe the band overshoots, the ones which go above some percentage alpha of the query q for some duration between the rising time and some fixed duration t1. And we're going to observe on the plateau from t1 to the end of the plateau how much offset you may have. So can you be up or down with respect to the query q by some factor beta for some amount of time. So we're going to observe overshoot, offset, and rising time. So formally, this is defined using STL with aggregates and sampling operators. So basically, you have the classical STL modalities, globally, finally, until. You have formulas and real value terms, but you have also aggregates, meaning that you can observe some function on the states for some duration AB from a current time t that you're observing this formula. And the aggregate you're going to use is, for instance, minimum and maximum of this signal over AB from your current time. You have also until operators and if then else operators, which are used to encode these observations. I'm just going to give you examples. So a full classic and robust semantics have been given to this STL with aggregates. And these are the semantics which are encoded and implemented and that measure the performance of the controllers. So just to give you an idea of these of the expressivity of this STL with aggregates, you can see a signal in blue x, and on 0, 1 max of x is in orange. So you see that for 1 second in the future, you're looking at the maximum of all the signal within this 1 second future window. And you see that the maximum is going to be here in orange, and then there, and that sort of things. And the minimum on the 2 seconds in the future is going to be the green signal here. So you can see other aggregates here, like this until operator. So you measure when y becomes positive, you measure the maximum of x within a future period of 1 and 2 seconds. Okay, this is a last example of a sample until operator. It's pretty much the same spirit. looking at when the signal Y is becoming positive, and look at the value of X within a future time window of 1 and 2 seconds. So this allows us to encode what it means for a signal to be stable. So it means that basically the maximum, the aggregated maximum on some window of t seconds minus its minimum is going to be less than some threshold. And then you can encode what is to be stable after having risen for some time. So this allows for encoding this rising time and these overshoot and offset um, uh, um, um, performance evaluation formulas. And then directly implemented as the robust semantics of these STL formulas, the code that does the performance evaluation directly on random queries of 20 seconds. Okay, so an auxiliary rate signal will be called acceptable if it does not overshoot a stable query queue by more than alpha% of the step size in the time window 0 T1. So T1 will be 0.5 seconds in all the experiments. Alpha will be 10%. And if it doesn't stray away from a stable query by more than beta%, which will be 5% in our current reporting, of the step size on a time step between 0.25 seconds and 0.5 seconds. So it allows also for the rising time to, I mean, the signal to have risen up sufficiently to measure things coherently. And so the rising time is just going to be this formula with these aggregates, which are going to measure when you are stable enough after a rising, and it's going to look whether the signal, the difference between the signal and the target queue is less than some gamma, some portion of the query queue. So as soon as it's not less than this and it's still rising up, then it's the time at which you've it's a rising time where you are close enough to the query. And okay. Okay, so the experimental setup I'm going to give you the results of is as follows. So we coded the full reinforcement learning mechanism and performance evaluation using Python, and the base also that we have a reproducible experiment. So the code, the source code is open source code that you can find here, and it's based on the on TensorFlow and Stable-Based Line Reinforcement Library. And as we wanted to test many different hyperparameters, we used a Kubernetes cluster that could run in just half a day the something like 2 months worth of computation. It's 2 months worth of computation because for each of the 240 hyperparameters we wanted to look at, each 3 million iterations of the reinforcement learning was taking on one processor between 3 and 8 hours. So you see, we tried to be fairly exhaustive and try to experiment on a wide number of hyperparameters. Of course, this produced an enormous amount of data and controllers. So we used Hyplot to look for the best controllers. So basically, for some filtering numbers, which are just actually the robust semantics of these STL formulas I was mentioning before, which measure the average overshoots and maximum overshoots and the rising times, the average rising times, etc. So we put off some sort of filters on these measures to get the best measures as possible, better than the PIDs anyway. And we are trying to filter the architectures by number of neurons, number of layers, and different conditions. And browsing through this enormous database of controllers, we could find the very best controllers, and which always are best with respect to the average overshoot, which is the average per all episodes used for evaluation, performance evaluation of all the average per episode of the overshoots. So the average, the maximum overshoot, the average and max offset, the average and max rising times, for all of these queries for performance evaluation. And they're going to also be best for what we call OK offset, overshoot, and rising times, which is when you don't go further than the alpha, beta, or gamma percent of the rising times you wanted to find, or overshoot or offset you wanted to have. Okay. So when you want to compare with PIDs, you have to see that PIDs are actually in general fairly slow. Even PID2, which is much more aggressive, reaches within 5% of the target for only 70% of the queries. PID1 is far too slow, so it just manages to rise on time the target for 8% of the queries. It's really slow rising time, almost always greater than 0.45 seconds. So we actually compare with respect to PID2, which is much more aggressive because PID1 is too slow. Of course, being slow means that you have a good overshoot success rates, because for the very rare queries where you manage to go to target, then you've gone so slowly that you don't overshoot too much. So the offset success rate is not good at all for these PIDs because the conversion is slow. So you have good overshoot, but bad offset and not so good rising time. So you can see, I mean, where the PID goes for this orange signal, it's fairly slow to reach the target here, but of course the overshoot is very small. Okay, so we're going to report the performance of the neural net controllers we have. In nominal mode, we're looking at the nominal trained controllers under non-nominal conditions, so some sort of robustness. And finally, we're going to discuss the non-nominally trained neural net controllers. So in this table, I'm going to show you, you'll always have the green numbers, which are the best ones, the blue ones, which are going to be the second to best, almost as good controllers, let's say, and the red ones, which will be the much less good ones. So you can see that with respect to rising time, as you can expect, the neural net controllers are much better. They give you much quicker control. The OK rising time is almost 100%, whereas the best PID is at 70%. And the average rising time is extremely small, less than 1/10 of a second. It's not the case for the PIDs. It's always like 0.4 seconds. And the max rising time is very good as well. For the offset, it's also very good. I mean, much better than the PIDs, all in red, with a large offset, which is possible. For neural nets, it's always almost always okay with an average offset which is very small. So you see that TD3 is not as good as the rest, which is a bit strange actually. It's supposedly a bit better than the old DDPG and a bit less old SAC. We'll discuss of that at the end. And for the overshoot, you see TD3 is even worse, but then the rest, DDPG, SAC, and even PPO trained neural nets are very good. So of course, PID2 is a bit better because it's so slow that it doesn't overshoot basically. Okay, so you can see what it looks like on real queries. You see the difference between a SAC trained 2 layers 16 neurons neural net with respect to the PID2 controller. So it's fairly slow. You see it's almost on target everywhere, but still you see some very minor spikes every now and then. And we'll discuss of that at the very end. So basically what we find is that we have a few very good controllers, 2 layers or 4 layers, 32 by 32 up to 64 by 64 neurons per layer. And always SAC and even DDPG trained neural nets. TD3 and PPO have been quite disappointing. So always some spikes, even with SAC regularization. SAC does some sort of entropy regularization, but doesn't eliminate all spikes. So the convergence of the training algorithms is very good for the best controllers, like the SAC 32 times 32 neurons. And you see 1 million iteration on, it's always extremely good for all measures we have. the interesting point is that the Markovian state of dimension 7 is not so good. I mean, it's even the worst of the performance we observed. The best one is always the smallest dimension 3 with just the difference between the target angular rate and the angular rates on PQR. And basically, we don't really need to observe anything else. And so it can be explained because it's non-Markovian, but the rest of the state is sort of second order in the dynamics. And the fact that we use the smaller dimension implies that we have a much better sampling, of course. So the neural net architecture influence, you can see that basically 4 neurons per layer, you can use as many layers you want, it never sort of works. And then from 2 layers on, they all are quite good enough. You don't have much better things with 3 and 4 layers as soon as you have at least, let's say, 16 neurons per layer. And training converges faster actually for the deeper layers, the deeper neural nets. That's the only thing that is a little better. When you look at the robustness of the controllers, so if you have a partial power loss or a wind gust up to 10 meters per second in some random fixed direction, you see that you have some degradation of performance, but not so much. They are very robust. You see the best SAC-trained controllers, the OK rising time is almost the same as for nominal conditions, even with power loss. You lose a few percent, but it's not much more. And the figures are not much less good than they used to be in the nominal conditions. You can observe this for all offset overshoot measures as well, as you can see. And you can see that PIDs do react very badly to wind gusts and power loss, especially power loss. They degrade even more than neural nets, which almost don't degrade. Okay, so SAC-trained neural nets are much better than 2PIDs and much better, exhibit much better robustness than the PIDs. So when you try to improve on this by training in non-nominal conditions, you see that actually you don't have better controllers. When you test under potential motor failures, the controllers which have been trained under these partial motor failures, you have good controllers, but they don't have the same success rate as even the non-nominally trained controllers under the non-nominal condition. So that's a bit disappointing, and you can see that for all performance measures we have. Also, in nominal conditions, you don't get very good controllers. It's a bit less good than the ones which are nominally trained. It doesn't degrade too much, but still. Okay, so wind gust, it's the same. We observe the same sort of problem. It's not as good as the nominal trained controllers under non-nominal conditions. So yeah, we're going to discuss this, but it's not really as good as expected when we try to improve the situation by training under non-nominal conditions. Okay, so it's all measures that exhibit the same performance degradations in non-nominal trained controllers. Okay, so what did we learn from this? First, that the training data, you really have to restrict to a good subspace. You don't need to be fully Markovian. If you look really at the dynamics, at the effect of each state on the dynamics, and the 3-dimensional space was here much better than the rest. Also, you get better sampling, so it's all for the best, really. Also, the importance of having a good query generator is essential to have realistic sort of signals to train onto. The controller is exceedingly important. Training algorithms were a bit disappointing by TD3. We have no good explanation for this yet. SAC seems to be a little better than the DPG because probably because of anthropy regularization. The strange thing as well is that it's not as simple as one could expect to find a good controller. Out of 5,000 controllers, we had just 9 which were exhibiting really good performances. Many of these other ones are not really that good. The very last 5% performance are really very hard to get because of these spikes we observed on each of these controllers. And these spikes, you can spot the problem. It's due to spurious correlations between the different axes, pitch, roll, and yaw. And further experiments showed that if we separated out different controllers for different angular rate controls, it behaves actually much better. So small and shallow networks actually were best trained and behaving best. You don't really need to go into very deep networks and very big networks either. They exhibit also all very good robustness to non-nominal situation, and that's most certainly due to the fact that we train these controllers on a very wide distribution of initial states. So they observed very different situations that account for this robustness when they see strange states because of wind gusts or other problems. But then we really have to understand why we didn't manage to train neural nets under the nominal situations in a good way. What we observed was that we had to balance things between training on sufficiently many non-nominal data, but avoid overfitting to these non-nominal cases. And we never quite solved this balancing problem, and further work is needed on this. So the conclusion, these neural net controllers are very good controllers indeed, very robust. That's really the hope we had on these neural net controllers. Of course, they depend on many more coefficients and basic PID controllers, so they can code many different sort of situations, but still some more work is necessary for understanding how we can improve the situation by training under non-nominal situations. An immediate step also to improve on the performance of these nets is to use our STL-based performance evaluation to actually derive reward functions so that we can improve on the training specifically for these performance measures. Some experiments in the literature have been carried out by other authors, and we hope to be able to do this later on. And this hope is also linked to the hope that we started actually some formal validation with reachability analysis of the full closed loop, and training using specific formal performance reward functions, based reward functions, means that we can hope for better formal validation at the end. Okay, thanks. So see you on the live presentation soon. Bye.